Hello, everyone. Welcome to another F-Sharp Essential Lectures lesson. And for today, we're going to be covering one of the almost the last few last lessons of the course, which is called Object Programming in F-Sharp. And we will be covering class type and interfaces, and also we will be covering recursion. So just a little bit of reminder, last week we covered improving your domain models, and so you can see the video that was uploaded today. And so yeah, if you want to check out what was about the session, please have a look at this one. And if you are in YouTube and you want to check our playlist, there's also a dedicated playlist in Amplify and F-Sharp YouTube channel. So yeah, please check those out. Yeah, without further ado, I'm going to give it to Ian so he can give us a lecture about object programming in F-Sharp.
Okay. I think you should be able to see my screen now.
Yes.
Okay, so welcome to session 10. Can't believe we've got this far through already. It's only 2 weeks after this, and then there'll be a whole load of other things organised, I'm sure, to take you way beyond where we've gone with this over the previous 9 weeks and where we're heading. So the agenda for today is I'm going to do a quick recap on last week, and then we're going to move on to object programming. Primarily going to look at classes, interfaces, and also equality as well, which is quite an interesting topic. And then we'll move on to recursion. Recursion is one of those things that in proper functional languages you do a lot of, but you tend not to do so much in F#. But it's still a nice tool to have. It's still a nice it's a nice thing to know about. So let's quickly do a recap on session 9. So we talked about improving your domain model, particularly looking at value objects rather. So removing this primitive of session. So on the screen there, for instance, I've got a simple record type, which is a customer. So we've got an ID of a GUID. We've got a name, which is a string, an email that's a string, and it's fine as far as it goes, but it's a little limited. When you've got systems you've got customers, you've got products, you've got various other things, you'll have IDs on there with GUIDs. It's very hard to know, or it's very easy to make mistakes with these. So one of the things that we can do is try to make it a little more domain strongly typed, as opposed to just strongly typed to the language itself. And then you've got things like a name. Should you be allowed to have a name with no characters, for instance, or do you allow, I was going to call it foreign characters, but illegal characters or something like that? And things like email. Certainly the subset of email is not the whole set of strings. It's a tiny little subset of things. So one of the ways that we can do that is to use a single case discriminated union. So we've used discriminated unions already, to do all sorts of things, to offer options. So if something's odd or even, that could be a discriminated union. But a single case is where there is only ever going to be one particular case. So we'll take the GUID first of all, and I'm going to just create a simple single case discriminated union called customer ID, and I'm going to give it the same case identifier as the type, and then the data is going to be a GUID, and then I can change the type there to be a customer ID. So really simple. And that means now that when I create a customer, so if I go, oops, I can't just go name equals. So the compiler is telling me that I can't do that because it's expecting it to be a customer ID. So all I need to do to fix that is to use the case basically as a constructor. In this particular case, I get a little warning here, so I have to because of the brackets, the parentheses rather. So I'm going to wrap those in a set of parentheses. Okay, I can prove that it's the case constructor and not the type that's used. So if I rename that, you'll see that that no longer works. So if I change that to X, so that's how I know that that works. So that's great for simple things like a GUID, but what about the email? Okay, so the email has rules. So I'm going to use the active patterns that we used in a previous session, and I'm going to create a type for email. String. I can change that to email, and then I need to use the case constructor again to set that. So we're back up and running again. But I talked about having some checks, some rules. So one of the things that we can do is we can force people to, instead of using the constructor, to force them to use a function. So one of the ways to do that is to set that as private. Right, but there we go. And create our own little module called email. It's just convention to do it this way, to have the name of the module the same as the name of the type. So I'm going to have a function called value for extracting the value. So that's going to be, so I'm just going to pass it in, and that equals so I'm just going to pass that into an anonymous function, and then I'm going to do a pattern match based on getting the data out of the single case discriminated union. So in this case, it's going to be email, and then I'll get access to the data. Well, that comes out at the other end. So that's how I extract the value. And then I'm going to create a little function called create. And in this particular case, all I'm going to do is I'm going to just create it for the moment, just to prove that it works. Okay, so the reason that that I'm not getting an error, even though that's private, is because that email type is still in the scope of this particular thing, this particular value here. So if it wasn't, I'd get an error here, but in this particular case, I'm not. So if I I'll put this into its own module. All my pipes. So now I'm getting some errors. So if I open my types, I've got the email back. Now you can see that I can't use the constructor because the constructor is private. So what I have to do instead is I have to use email.create. And that fixes that problem for me. And then when I want to extract the data, so I can do, let's email equal, so I'm going to do customer dot email. And then that, I can use the dot value function from the email module to extract the data. So the only other thing now I need to do is to do some is in the create method, in the create function, I need to test the input against my pattern matching. So if I match the input with, so his email, I'm not interested in the output. And if that's the case, I can do input. So I'm going to return a result type from this. Input is, what's an email? Okay, so that's basically what we did last time. Obviously, I need to fix this up because this is now a result. So I can't do a simple creation like this. So I'd need to have a little function that takes all of these things in. So we're going back to the validation stage from here. So the only other thing that we covered was errors, and we looked at the map error function. So if we remember back to map, so map is a function that takes a function and in this case result.map is a function that takes a function and a result. If I do match the result with, so if what I pass in is an OK, then I apply the function to the value that's in that result that's passed in. And I wrap the result in an OK. And if it's an error, it just gets passed through. The map error does exactly the same thing, but it does it for the error path rather than the OK path. So if I do We do exactly the same. Except OK gets just passed straight through. And then we apply the function to the error. So if you look at the signature, map is a function that doesn't return a result, the effect in this case, and it takes a result of A or C and returns a result of B or C. So the function just gets applied to the OK path. And then on the map error one, it works the opposite way around. The thing that gets changed is the error. So you have a specific error for each of your functions, and then when you have a function like validate, you'd have a particular error type for that that would use the other error types as data, and you'd use the map error to map the error from the original type, the original error type, to your validation error type. So that's a quick recap of what we did last week. So now on to objects. So I generally view F# as being a functional first language. So it does lots of other things, but it's functional first. But it has a very strong object programming model. I nearly said object-oriented programming model there. Trying not to do that. It's a functionally oriented language. So it's object programming rather than object-oriented programming. So they are really, objects or classes are really useful for particular things. So three particular things that I think are useful for them. So you can hold or mutate state for periods of time. That's much easier to do in a class than it is in a functional data structure. If you've got an internal representation that's different to the external representation, that again is much easier to do with the class. And if you deal with a lot of OO style libraries, then it's often easier to work with classes and objects than it is with functional data structures. So let's start with a simple idea. So what does a class look like? The simplest class that we can do would be something like something that took no inputs. So if I do my class so the difference here is, so far all of our types have never had parentheses after them. So simple class, so that is the constructor in effect. So this is an empty constructor. And then we can add a basic property or a method or something similar. So if I trying to think of what I could do that would be sensible for my class. So we add methods by using and properties by using the member keyword. So I'm going to do I'm just going to return a string. So to create it, You don't need to use the new keyword when you instantiate a class. You do need to use them when they're iDisposables. But if it's not an iDisposable, you don't need to use you don't need to use the new keyword. So that's created a class, and then I can do so if I just run that in interactive, it tells me that message is hello. So not very useful, but that's the basic idea of a class. So let's look at something a little bit more complicated. So I'm going to use the GPS coordinate that we looked at last week, and this time I'm going to do it as a class. So we create the type to GPS coordinate, and it takes two parameters in tupled form. You can't use non-tupled form with classes; they have to be in this format. And then we have two properties, and I'm setting the properties to the values that are coming in. So let's create a coordinate. Let's go back to Null Island again. So that's a GPS coordinate. And you notice it's telling me that I have to give them both of the coordinates. I have to give them both of the arguments. So Null Island is at 0 and 0, and I can get at the data by doing what you'd expect. So I can get at the properties. Okay, so that's pretty much akin to a C# record in effect. So if I do that, I get 0 and 0. Everything works as I expect. So let's go on to the first thing that we can do differently. So let's have a mutable property. Let's take that, paste it down here. So I'm just going to comment that out. So I'm going to add, so at the moment I've got latitude and longitude. I'm going to add elevation to this as well, so height above sea level. I know it's not part of a GPS coordinate, but it's something that we can quite easily reason about. So member val and as I'm not passing the data in, I need to give it an initial value. So I'm going to say 0, and then I'm going to add with get and set. So what I can now do is let's go with, so that's my initial elevation. And then I can do so the way to set data using mutable data is the is the back arrow, so less than and the minus sign. So I'll set that at 25 meters. Let's copy that and do that. Okay, let's just run all of that. So you can see there that it's set the elevation. So that's mutable property. So using the with get and set, you can extend those as well. So you can make them so that they can have logic in the getters and setters as well. But I'm not going to show that. That's slightly more complicated, but not much more so than that. Let's copy that. Knock that out. Right, so next one I'm going to look at is object initialization. So one of the things that you can obviously do in C# is you can have you can set some properties and not all properties when you create your object initially. So you can do that in F# as well. And the syntax is slightly different, as you'd expect. So the only change that we need to do here is we can add, so if I want to set the elevation in the constructor, I can just add it, but I need to specify the name of the property that I'm setting in there. So I no longer need to set those. So if I run that, I should now see that the elevation is set to 25. And if I don't set it, it remains at 0, which is what it was set in the definition. So that's one way of doing that. We also have optional properties as well. Let's comment on that so I don't get any warnings I don't expect. So what I can do is I can add elevation to the constructor. There's a decimal. And I'm going to put a question mark in front of it. So if I now run that, and if I run these two here, actually I'll just run all 4. So the mistake I've made here is I'm not actually using the elevation. So what I need to do is I need to take that and I need to put that into the initial value. Well, that's better. And you'll see that I've suddenly got some options coming out. So this is using options to say if it's set, then it might be a sum of something, and if it isn't set, it's going to be none. So if I run that, so I didn't set it when I created the object here. So that's why elevation is none. And then if I do set it, and this time because it's a named parameter in the constructor, I don't need to add it to the constructor here. So if I do that, now comes out as sum25. You can have multiple constructors as well. I'm not going to show that, but as well as the primary constructor, you can have multiple other constructors as well. So I'm going to do, as part of this, I'm going to do both objects and recursion. I'm going to do FizzBuzz in both, just because I like FizzBuzz, I suppose. So let's have a look at how we'd create a FizzBuzz class. So this is my initial example. So this is the functional one, a function rather than a class. So what I'm going to do is I'm going to wrap this function up inside of an object, or a class type rather. So type what is that there? I'm going to have a member. I'm going to have a method called calculate. And all I'm doing is just call out to the existing calculate function that's already there. So in terms of scope, you can't get at the internal calculate function from the outside. The only way to use it is using the calc. Can't spell today. That looks better. Right, so the only way to get at that internal calculate function with the lowercase is to use the calculate method. This plus equal. What I'm going to do is I'm going to do a quick list of 20. Do a list.map. And then I'm going to do FizzBuzz dot. Let's move that inside. Oops. I can't type. So let's prove that that works before we go any further. That looks reasonable. So fizzes and buzzes in the right sort of places. One thing that I can do here is I can take the mapping. So I'm going to copy that. I'm going to paste that into there. I'm going to create an input parameter for the constructor, and I'm going to pass the mapping. In there just to make it slightly more usable. I think that's everything. Let's quickly just run that again, just to make sure that looks like it works. Okay, so we've got any questions up to this point?
No questions so far. I answered one in the chat about the to the new keyword on the I disposable that you mentioned. So yeah, that's correct.
Yep. Okay, so that's basics of objects. So the next one to move on to is interfaces. So do for an interface. Oops. I'm trying to remember which one I wanted to do for an interface. Actually, the easiest will be to do just to take this. This is the simplest one to go with. So I'm going to create my my interface for FizzBuzz. I'm going to call it my apps. Calculate, and this takes an and returns a string. Okay, so there's nothing special on an interface. So there's nothing that defines it as a as an interface, other than the fact that that there's an abstract keyword used here. If you want to create an abstract type, there's an attribute called abstract class that you can use, but I'm not going to create an abstract class, so I'm just going to create an interface. So to use that, I need to tell it to use the interface. Which my brain has forgotten about for a second. Just give me a second.
One of the things that I when I started learning F# was that I noticed that the object programming model that F# offers is really based on not adding more keywords to the language, but rather supporting that through attributes. So that's why, as Ian said, you will have attributes for abstract class, you will have attributes for sealed class, all that stuff. So you have your class definition, and then depending on the attribute that you use, you will convert that class to its representation that will be compiled to abstract class or to sealed class in the C# side. So yeah, and to be honest, I really like that approach, that design, language design decision, because you are not really it's not support the object programming, culture as such, but just to give you the enough that you can actually do most of the stuff that you can do in C Sharp, if not everything.
Yeah, I mean, at the end of the day, the object programming model in F# is very powerful, but it's very much from my perspective, it's a use it where it makes sense to use it rather than being the first approach that you use. So it's also a lot stricter as well in some things. So to use the interface, I've created the interface. The I in the name really doesn't matter. It's it's just convention that people do that, but you don't actually need it. So we we're basically defining the function signatures that we're expecting for that interface. So using the abstract and then calculating it's a function that takes an int and returns a string. And then to implement that interface, we use the interface keyword with the name of the interface, and then we implement the member of that, or the method in this particular case. You'll notice now that that calculate has a compiler error, and it's telling me that the type FizzBuzz does not define the field constructor or member calculate. So in C#, this would be okay because you get implicit casting, but in F# you don't. So we actually need to cast it to the interface, which sounds like a retrograde step, but actually it's part of the F# being very explicit about, you have to say, I know what I'm doing, and do it rather than just relying on the compiler to think that that's what you wanted to do. So to do that, we need to upcast to the interface. So the quickest way to do that is to use the upcast operator, which is : greater than. And in this particular case, I probably wouldn't do this here because that's going to do that for every single one of these items from 1 to 20. So it's going to do it every single time. So I'd probably do it there instead. So it only does the cast once. So there is another operator as well, which is if there's an upcast, there's also a downcast. So the downcast operator is a question mark in the middle. So if you want it, if you have an I FizzBuzz and you want to get a FizzBuzz, then you'd use the downcast operator. Okay, so I've actually done the implement there in one go. The other thing we can do with interfaces is we can use them as parameters in functions. So let's copy that. Okay, so if I create a new FizzBuzz, with the and then I call do stuff with FizzBuzz. So I don't know how much of that I've ran. So if I run that, let's so you'll notice here that the do stuff function takes an iFizzBuzz, but I'm passing in a FizzBuzz. It does actually do an automatic, an implicit cast for you in that particular situation. So you don't. So I didn't need to cast it to an iFizzBuzz. It's done it automatically. So that's interfaces. So they're supported as well. Not a lot else to say with those. So there is something that we can do with interfaces called object expressions. So I've created a simple logger type. So this is a logger interface, and I've got two abstract members called info and error. Actually, I'm surprised that let me get away with that because I missed the member keyword. Maybe it's not necessary any longer.
Yeah, it's not necessary.
Yeah. Well, I'd have got a warning, I suppose, or a compiler error if it was absolutely necessary. Okay, so if it's no longer necessary, I might as well take it out. So if I create an iLogger that has two methods on it, so string to unit, both of them. So they take a string, just don't, in this case, we just print stuff out. What I can do is instead of creating an explicit type, I can just effectively create a type on the fly. So I can just create a new iLogger with some basic implementation. So I tend not to use these very much, but I was talking to Edgar before the session, and he did a lot of Xamarin work, and apparently this is something that you do a lot of in Xamarin with F#. So might be worthwhile talking to him if you're interested in this particular thing. As I say, I don't really use them that often. I don't know whether that's just because I've not come across situations where they're necessary, or
This is mostly a rare case because when you are consuming iOS APIs or Android APIs, there are protocols that maybe have, I don't know, 10, 15 members that are declaring those. So you don't want to basically, create a class and then implement the interface, and you don't want to add an implementation for all of the different for those members. So what you do is basically, as you are showing there, you create a type of the fly there, and you just say new iLogger, and you only implement the one that you want rather than basically do that.
So do you need to? So you'd have to create your own interface.
Yeah, but I think it depends of how they are marked in the Xamarin world. So in this case, you need both because both are defined there, but they are defined in a different way there.
Okay. So yeah, it just depends on your your usage. I haven't come across situations where I've needed to really use them, so it's not really something I'm an expert at in any way, shape, or form.
Yeah.
The things that I tend to use them for are like iDisposable. That ends up being a very common one for me. Because like a lot of times, some things want to return some type of iDisposable, and in something like C Sharp, you have to define a whole class around that. Whereas usually iDisposable just means you need to call some cleanup code. And
Yeah.
for lack of a better term, iDisposable is literally just a function. That's all it is.
Thank you, Jimmy. Okay, so the final bit that I want to do with objects is equality. Now, one of the problems that we have is that most of the types in F# have structural equality, which means if they look the same, they are the same. And this doesn't work with objects, with class types, because they use reference equality. So they work pretty much like classes do in C#. So if you want to use a different type of equality, then you have to jump through some hoops, and that's exactly the same as you do with C#. If you want to change the way that equality works, you need to use get hashcode, override the equals, override use the IEquatable interface, and also you probably want to override the equality operators as well. So that's what all of this is doing. So if we take our simple coordinate function, coordinate class rather, so we've got a latitude and a longitude. I've just moved the equals function, so just have a local internal function here that just does that just checks to see if one's null, then it's not, they're not the same, because obviously the one that you're testing for equality can't be null. And then otherwise it's checking just to see if the latitude and longitude are the same. So we've got the same members. We've got so the allow null literal has to be there because normally you don't get nulls in F#, and it's just forcing it to allow a null to to be able to use the is null function. There's a built-in hash function as well for hash code. In the equals function, we're testing, this is the pattern match on type. So it's checking if the type is a GPS coordinate. And then it just tests to see if it equals the other one. That's about it, I think. The other interesting one here is the this keyword. It doesn't mean this as it's used in C#, for instance. It's just a name for that particular instance. So it could be anything. It's just convention that most people tend to use this, or they use an underscore if it's not necessary, if you're not actually going to use it. So that then means when we've done all of this, that we can then create two instances and compare them, and they do actually come out as being equal. So if I get a true at the bottom there. So two instances are equal. Okay, any questions from that particular section?
No, there was just some comments about that they were also useful for testing mock objects regarding the object expressions and like no.
Okay, again, another thing that I don't have a lot of experience of. Okay, so the last thing I'm going to cover with classes or class types and objects is encapsulation. So remember, one of the things I talked about with why you might want to use class types is if your internal representation is different than the external representation, and if you've got mutable internal data. And what I've got here is a recently used list type. So I've created an interface, and it's a generic interface. So that's the obviously the generics thing there. So there are two members on there. So there's an abstract function that takes called add that takes a t and returns a unit. So it just adds it to the to recently used list. And then there's an items property that allows you to return a list of the items that are in the recently used list. And that's all it does. So it's a class type. It takes a capacity as a constructor, as a constructor argument. And then internally, we've got a resize array, which is a .NET or C# list called a resize array in F#, with a capacity of whatever we decide to use there. There's an internal function add, which just basically manages the recently used lists. So if you imagine if you had a list, and what you're doing is if the item's already in the list, you want to remove it. Well, you just want to remove it anyway. You then want to check to see that you haven't reached capacity. If you have, you remove the oldest one, and then just put the new one at the top, and then you just add the new item. So that's all that thing does. We then implement the interface with the two things on the interface. So the add method and the items property. And all I do there is convert the internal data. So resize arrays a sequence. It's an IEnumerable in effect. Convert it to a list and then reverse it, because the resize array works in a different way to the completely different order to the order that a list in F# does. So return it the opposite way, so it returns the newest at the top. So that's my recently used list. So we've already seen that we can pass it into a function as an interface and just call things on it. That works fine. So I create a new recently used list of string, and it's going to be 5 items long. And then I'm creating my list. I'm going to convert it to the interface type. I'm going to add 3 items, look at what that items is like, and I'm going to just call a function on that, and then look at the items again, and then I'm doing a downcast at the end. So this just proves that the thing works. Oops. So I've added a red, a blue, and a green, and then I add a blue. So when I add the red, the blue, and the green, I should get a list of green, blue, red, and then when I add a blue, it'll obviously remove the blue and then put it at the top, which is what it's done. So that's just proving that thing works. But the important thing to note here is that we've encapsulated some state, some mutable state inside the class type, and then we've made it available via an interface. You don't need to use an interface. You know, we could have just made them just members of recently used list, but it might be that you want to you might want to write different versions of this recently used list. So that's as far as I want to go with objects. They're, as I said, they're very useful, very powerful. We've basically scratched the surface of what's possible. You know, you can do an awful lot more if you want to. My advice would be, if you want to do an awful lot more with it, just stick with C#. That's designed for object-oriented programming. You know, if you use the object programming features from F# wisely, they're very powerful, very useful, and you will end up using them on occasions. So don't try and fight the system. Sometimes things are better done in an object style, in an object programming style, than they are in a functional style. So it's not about the purity of the language, it's about getting stuff done. So on to recursion. So recursion is a really simple idea. It's a function that calls itself. So let's do a simple function that sums the numbers from 1 to something, 1 to n. So to define a function as recursive, we use the rec keyword. Okay, so there's some things that I need to do with this. When you're calling yourself, you need to make sure that there's a point at which the thing will stop. Otherwise, it will recursively carry its on forever. So there must always be a way of stopping, unless you want your function to continue forever, which you may or may not want to do. So in this particular case, if I'm doing the numbers from n to 1, or 1 to n, whichever way you want to look at it, and I'm doing a simple sum, so I'm just going to add them up, then my stopping point really is probably going to be when n is 1. So if I start at n and go down, so if I start at 8 and go to 7, 6, etc., once I get to 1, I know that I've got a 1 at the end there. So let's try that. So let's do, so match n with, so I'm just going to return 1 if that's the case. Otherwise, if it's not, what I want to do is I want to return n plus the sum of n minus 1. Okay, so let total equal sum 10. So if I run that, I get 55, which is the correct answer. Unfortunately, it's a very bad thing to do this. So let's think about what I'm actually doing here. So the first step, I'm doing sum of 10. Step 2, I'm doing 10 plus sum of 9. So actually, get that up. So the third step, I'm doing and you can see that carry on and carry on and carry on until I reach I think it'll be step 11, where I'll end up with I'm not going to match up the parentheses. One, two, three, four, five, six, seven, eight, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I end up with that. And the reason that it does that is it can't actually do the calculation until it's carried out every single small calculation. And it can only do that once it reaches 1. Once it reaches 1, it can then go back up a step, back up a step, back up a step, and finish the calculation off. So it's very inefficient. It's also, it can blow your stack trace as well as it gets bigger and bigger and bigger. So this isn't a good idea. Obviously, if you know you've only got small numbers, it's not really a problem. But if you haven't, then it's probably not a good idea to write it like that. What we're doing instead is use tail call optimization. So to stop this sort of thing happening. So let's take our function again and think about how we can rewrite this. Okay, so what we want to do is we want to basically have it so that we don't leave any calculations undone in between the steps or in between the loops on the recursion. So what we're going to have to do instead is to think about how we're going to do this. Well, so to do this, we need two things. We've already got one thing, which is the what the current value is, but we also need to have a running total of the sum as well as we're going along. Now, to do that, I can have, so that's my initial value, and then I can have a total function here. So so that's n, so I've got, that's my total. So if I run sum of, that's the next value, and call that correctly. And the other thing that I need to do is, instead of returning 1 when I reach the end of the function, what I actually need to return is the total. So that equals that, and my total when I start is going to be 0. So let's try this one. Okay, so that doesn't quite work now. So I need to change this to be 0. So we now got 55. So this is tail recursion. I can actually tell the compiler in version 8 of F#. There's a new attribute called tail call, which the compiler can then use to say to verify that your code is actually using tail call optimization or not. And in this case, it is. I don't particularly like this style. Although this is quite easy to do, I don't like the fact that I have to pass in the second parameter rather than the first one. There are some other problems with it as well. So this is only allowing me to work out items from 10 back to 1. What happens if I had just had an arbitrary list of integers that I wanted to get the sum of? So this particular style I don't particularly like. I'd rather that I can call it the same way as the first one, so sum of n, and I can hide the fact that there's an initial value under something else. And that's what we're going to do with this. So just comment that one out at the moment. So in this case, I don't need to use I'm not going to use the recursive function in this. I'm going to use the recursive function as in an inner function inside this. So let's sum of n equals, and then I'm going to do an inner function I'm going to call loop, and that's going to take, so that's going to have my I'll call it next value and the total. And that can just take that with a few minor changes. Okay, and instead of me calling, instead of me adding the extra there, I actually need to call this function. So I can just call loop with n and 0. Yeah.
I think you might have to call loop rather than sum, the bottom.
Yes, you're correct. Thank you. Oh, there you go. Right. A little bit confused. Yes. So you need to call the recursive function, and the recursive function in this case is called loop. Okay, so the advantage of this is it allows me to call that. I don't need to know about anything about the internal workings of the of this particular function. So if I run that, I just got confused. So I'm going to kill the session off and start again. Ah, might be heading into infinity here, I think. Right, let's have another go. Yay. Right, that's better. Okay, so that's just taking that end. But remember I talked about just taking an arbitrary list of things. So let's try that. Okay, so if I pass in, so if input now becomes a list of integers. Okay, so that is my total. So that's my okay, so that now needs to match a I'm not sure I need to call that next now. So if I think about this, I need to be so the natural end for a list of things is an empty list. So that gives us a total. And if I'm here, I need to get I've got a head and a tail from a list. So if we use the pattern matching for head and tail using the cons operator, the name head and tail is they're just names. So that there becomes the tail. And I add head to that. So if I pass in an int list, I pass in the original list, I then get the list. If it matches an empty list, I get the total, which will be the original value of 0. Otherwise, I take the top item, I add that to the total, and I return the tail. Okay, that looks like it should work. Okay, and I need to pass in a list. Okay, so that now works as well. So the last one to do is FizzBuzz through recursion. So let's go and find my FizzBuzz function. I'm going to copy that over. Where are my recursion? Don't have the mapping. I need to get that back. Right. So let's have a think how we do this then. So I want to loop through the list. So I want to be able to call that so so what do I want to start off with? So I want to start off with that, and I want to output a string at the end of the day. So my initial starting point with the string would be an empty string. So therefore I need that to be what's left of my list. So effectively that would be my tail. I don't want to call it that, so I'll just call it remainder. And then I'm going to have the concatenated string. So let's work this again. So if it's an empty string, sorry, if it's an empty list, I'm just going to return that for the moment, but that's obviously incorrect. Otherwise, so we've got a tail and the head, and I want to go the loop, and I want to pass the tail out, and I need that with the wrong way around, head and tail. And I want to add that onto there. Why does it? I'm looping through those. What's the purpose of the N? I haven't got to that yet. Okay, so let's have a look at this. So what do I do with my logic? So if it's a that's the thing that I'm passing around. I then need to say I don't want the head bit. The head bit is actually the tuple. So therefore I need that. So if n so let's deconstruct that as so that's the divisor and that's the message. So if n is divisible by the divisor 0, then it returns the message, otherwise it returns empty string. Okay, and the only other thing I need to do is this last one. So if so does that look like it's going to work? So let's think about it. So if it's so I've done my so when I eventually finish, I need to return the end thing, which is correct. So I'm passing around the list and the concatenated string. So when a pattern match, I get the deconstructed tuple, and then loop, I pass a tail, which is the next item in the list, and then I concatenate an empty string onto there, or potentially the message. Right, that looks like it works. So let's try it. Try that again, 1 to 20. This dot map. And calculate. Fingers crossed. Yay! Success.
Let's try it.
That worked. First time.
We have a question regarding how will you recognize, let me read it properly. Would it be possible to explain why the tail call optimization is better? And yes, so that
So tail call optimization is better for 2 reasons. It uses a lot less memory, and your chances of getting a stack overflow are pretty much 0. Whereas if you don't use tail call optimization, so this example that I showed here was just 10. It's very, so if you did factorial, for instance, if you do 50 factorial with a non-tail call optimized solution, you'll get a stack overflow. Whereas if you do it with the whereas if you do it in a tail call optimized style, you don't, and it comes back within a fraction of a second as well.
So the question is, so for example, in line 22, how do I recognize in that line 22? I can recognize that I'm applying the tail call optimization on my recursive function because the SAMT is now there hasn't been we are not producing any computation on the returned value, so we are not
Correct.
modifying the value.
Yeah, correct. You're looping what you've got here matches
Exactly.
that. If that matches, there's no extra calculation to be done. So you've got calculations being done, but they're being done on each step.
Exactly. And the
So
difference,
it completes all the calculations before it goes on to the next step of the loop.
and the difference with line 6 is that in the line 6, then you are doing n plus sum t. So you are actually mutating, or you're actually computing a value on the return value.
Yeah, you can't do the calculation until you've done all of the calculations.
Yeah, that makes sense. Yeah. The
So-
attribute is also really useful, but Jimmy said something that's really interesting. Like you're not going to get the warning when you are at the editor level. When you are, when you apply the compiler, you first need to build it. Build the program in order to get that, because this is not something that the compiler can do it just on the fly. It needs to be built in order to actually execute the code.
Yeah, but obviously you generally won't be running things like this inside of a script file. You'll be compiling anyway. So
yeah, true. Yeah, I think that's the only question we have.
And that's it. So yeah, recursion's very useful. I've only done it with simple ints here, but they work with anything. And you can see why we use strings here as well, but you can use them with any type. You can have any number of extra parameters on there. You can just have a single type if you want to. It's up to you.
Yeah, awesome. That looks good.
Right, so that's it for session 10. Session 11 is computation expressions.
That sounds good. Can I take back the screen?
Yep, of course you can.
Yeah, thank you. So let me share my screen and just a little bit recap, like Ian said. So we have completed our session lesson 10, I believe.
Yep.
We have covered the object programming in F#, modeling in F#, and the recursion. Next week, we have the computation expressions lesson, which is about fundamentals of computation expressions and compound effects. And we have, after that, we have just one left, which is the using ASP.NET Core with web pages and APIs. So yeah, thank you very much, all of you that have been attending to the lessons. You have made it through, 10 weeks. We have learned a lot together, and we are really looking forward to complete the lessons. And also a big thank you to Ian for all the effort that he has put on to designing this table of contents, and also by providing an amazing book that you can check it online, Essentials F#. And as I say, if you want to rewatch the previous lessons and you want to go at your own pace, just go to our YouTube channel, Amplifying F#, and then go to the playlist, the F# Essential Lectures, and you will find all the content there. So yeah, thank you very much, everyone, and I see you on Friday if you will be attending to one of the sessions that we have on Friday. If not, let us know. Any feedback is welcome on Twitter or in the video, in the YouTube video tutorials. All right, without further ado, thank you, everyone, and see you next week. Bye.